Welcome, curious minds, to the deep dive. Today we're not just exploring some distant corner of the cosmos. No, we're diving headfirst into one of the universe's really big ones, one of its most profound mysteries. Have you ever stopped and truly pondered what dictates the colossal structures of galaxies? You know, the immense cosmic voids, the very scaffolding that seems to hold our universe together. We know gravity plays a huge role, obviously, but what if there's more? What if there's an invisible hand, maybe an unseen dynamic force, actively shaping everything we see and don't see? But if the invisible stuff isn't just inert, but, well, alive in some sense, vibrant. Today we're taking a really deep dive into a revolutionary concept, a hypothesis really that suggests dark matter isn't just dark and passive, sitting there doing nothing but pulling things gravitationally. No, this idea proposes it's a vibrant, charged plasma, a kind of fundamental blueprint, you could say, actively guiding how stars form, how galaxies get built, how the whole intricate cosmic web gets woven together. Our exploration today is guided by a truly thought-provoking paper.
It's titled, Is the Dark Plasma Universe Shaping the Ordinary Matter Universe? It's by J. Alfred, published September 2025. And drawing on years of his own really meticulous research, Alfred puts forward this, well, pretty compelling case. He suggests the dark universe mirrors our own in some fundamental, maybe even surprising ways. So what we'll do is unpack some surprising observational evidence that seems to hint at this dynamic dark matter. We'll explore these kind of mind-bending structures that really challenge our standard understanding. And crucially, we'll try to distinguish this dark plasma idea from other cosmic phenomena, because it's easy to get things confused here. Get ready for some serious aha moments, honestly, because this deep dive could fundamentally shift how you perceive the cosmos, right from the tiniest dark particle interactions up to the grandest cosmic structures. Okay, let's unpack this incredible idea. What if the universe is far more interconnected, more alive than we ever really imagined?
It's fascinating, isn't it? What's truly fascinating here is how this concept tries to pull together these seemingly disparate observations. You know, those little anomalies, the things that don't quite fit our standard models. And it offers a cohesive, almost elegant model for the architecture of the cosmos. It really moves beyond just thinking of dark matter as, well, missing gravitational mass. It delves right into its potential dynamic, interactive nature. This isn't just adding another layer, you know. It's suggesting a pretty fundamental reevaluation of how the universe is actually built.
I couldn't agree more. It really feels like maybe finding a missing piece of the puzzle, suddenly seeing it maybe illuminated.
Yeah.
So, okay, let's start with the core idea then. The dark plasma hypothesis itself. Now, J. Alfred's work in this area, it isn't brand new. He's been exploring these kinds of ideas for a long time, actually. Some previous papers go back as early as 2005. His research has consistently suggested that a significant subcomponent of dark matter doesn't just exist passively. It specifically exists as a self-interacting dark plasma, particularly when it's near ordinary matter.
Right, that's the absolutely crucial starting point. And when we define self-interacting dark plasma, what we're talking about is a plasma made of dark matter particles that possess a very weak, yes, but definite electric charge. Now, hold on, this isn't the electric charge we know, like protons and electrons interacting via standard electromagnetism. No, instead, it operates under what physicists call a hidden U1 gauge symmetry. Now, to simplify that a bit, imagine our universe has electromagnetism carried by photons, right? Well, the dark sector could have its own sort of parallel force carried by dark photons, maybe, which only interact with particles that have a dark charge. It's hidden because these dark photons, well, they just don't interact with our electromagnetic spectrum at all, so our instruments can't see them. And a gauge symmetry, that's basically the underlying mathematical rulebook that dictates how a fundamental force works, keeps it consistent.
Okay, so let me try and put this in perspective. If over 99% of the ordinary stuff, the visible matter in the universe, everything from stars, nebulae, even the gas between galaxies, if that's mostly plasma, then it feels profoundly logical, doesn't it? To wonder if the mysterious stuff we can't see, this dark matter, might also share that same fundamental state, especially if it carries its own unique kind of dark charge. It's almost like an elegant symmetry, isn't it?
It absolutely raises a profound question. It's a very logical extension of how we understand matter, really. If dark matter does have its own dark electromagnetic interactions mirroring our familiar electromagnetism in some way, then evolving into a plasma state becomes not just plausible, but, you know, a highly expected behavior under the right cosmic conditions. This completely transforms dark matter from being just this purely gravitational entity, a kind of cosmic ghost, into something with its own rich internal dynamics, its own complex interactions, and that shift in perspective, well, it could have truly far-reaching consequences for how we model the entire cosmos.
And those consequences, that's precisely what makes this hypothesis so compelling, I think. Because if dark matter does have these non-negligible self-interactions, it immediately stops being just a passive, collisionless, invisible cloud that just sits there, only acting through gravity's pull. Instead, it actually gains the ability to actively form complex structures, to exhibit dynamic instabilities, much like the ordinary matter plasma we see everywhere. That's a total game changer.
Exactly. If it's self-interacting, we're no longer stuck thinking of dark matter as just, a collection of inert particles drifting around. We're now considering it as a medium, maybe a cosmic fluid that could exhibit these incredibly complex phenomena, very much analogous to ordinary plasma dynamics. This opens the door to possibilities like, well, dark shocks. Imagine streams of dark matter colliding, creating energetic shock waves that ripple through the dark sector. We could potentially see filamentation, where dark matter organizes itself into these long, intricate, thread-like structures. And crucially, it could generate its own dark magnetic fields. These fields would then govern the flow and behavior of this dark plasma across immense cosmic distances. These are all, the definitive hallmarks of how ordinary plasma behaves. And the hypothesis proposes that strikingly similar dynamics could be happening within the dark sector.
Okay, this is where it gets really interesting for me. Because it turns out scientists are already seeing things, observations, that strongly point towards this kind of plasma-like behavior in dark matter, even without directly detecting the dark matter particles themselves, right? We're talking about observational evidence, these signature features of plasma dynamics being found in how dark matter is distributed and how it behaves across the universe. These aren't just like theoretical ideas anymore. These are anomalies in the actual data that are making people look for new interpretations.
Indeed. This isn't just pure speculation anymore. There was actually a significant consensus reached back in 2018 at the 60th annual meeting of the APS Division of Plasma Physics. They concluded that, and I'm quoting here, dark matter can behave like a cold, collisionless plasma of self-interacting dark matter particles and exhibit plasma-like instabilities with observational consequences. End quote. The key phrase there is observational consequences. These plasma-like instabilities, they aren't just theoretical predictions written on a blackboard. Their effects seem to have been directly observed, or at least inferred, through really detailed gravitational lensing reconstructions of massive cosmic structures.
So, okay, if I'm getting this right, we're not just imagining these instabilities, we're actually seeing their gravitational effects, like how light bends around massive stuff. And those distortions are telling us something really dynamic is happening in the dark matter itself. But there's a really important distinction here that J. Alfred's hypothesis makes, isn't there? These dark plasma instabilities, they wouldn't be as chaotic or, energetic as what we usually see in ordinary matter plasma.
That's a critical point, yes. And it really speaks to the, elegance of Alfred's hypothesis, because the hypothesized dark charge is thought to be significantly weaker than our standard electric charge. The resulting plasma instabilities in dark matter would likely be far less erratic, less chaotic. This lower level of energy dissipation means dark plasma could potentially form and sustain more stable, more enduring structures over cosmic timescales. And this distinction is crucial because it allows the dark plasma to potentially act as a stable sort of template for the ordinary matter universe, rather than being just a fleeting, turbulent mess that would quickly dissipate.
Right, okay. And this more nuanced understanding, it leads us to some really fascinating reinterpretations of cosmic events we thought we kind of had figured out. Like, take the iconic bullet cluster 1E065756. Technically, for years, that's been the poster child. The go-to example used to argue for purely collisionless dark matter. The standard story is, two galaxy clusters merge. The visible gas clouds, ordinary plasma, they collide head-on, get superheated by shocks, and lag behind because they interact electromagnetically. Meanwhile, the invisible dark matter halos, being collisionless, supposedly just pass right through each other, like ghosts, leaving the visible gas trailing behind.
That has certainly been the prevailing and very influential view, yes. However, there's a growing body of reinterpretations emerging now, challenging this simple collisionless picture. These suggest that maybe at least a subcomponent of dark matter might interact more like a plasma. Furthermore, observations in other really massive galaxy clusters, specifically Abell 520, often called the cosmic train wreck, and Abell 3827, which is known for its dark core, they present even stronger evidence, arguably. In these clusters, dark matter seems to behave more like collisional plasma, which is a significant departure from the simple collisionless model the bullet clusters seem to support so well.
And it gets even more compelling with Abell 3827, doesn't it? Because gravitational microlensing observations in that cluster, they've shown something really weird. The dark matter halos are actually seen trailing behind the stars within the merging galaxies. Now, this trailing, it isn't just a minor detail. It strongly implies there are significant drag forces acting on the dark matter. It suggests the dark matter isn't just sailing through smoothly, but it's hitting some kind of resistance, maybe from a surrounding dark plasma medium. That sounds like a massive clue for this self-interacting model.
Absolutely. If we connect this to the bigger picture of dark matter research, these specific observations, particularly that trailing dark matter in ABIL 3827, they directly challenge the simplest collisionless dark matter models. They really open the door wide for more complex self-interacting behaviors where dark matter isn't just a passive gravitational player, but a dynamically active one, capable of exerting drag forces, maybe dissipating energy. These aren't just isolated anomalies, they're data points suggesting a much more dynamic and interactive picture of dark matter than we previously assumed, pushing the scientific community to seriously consider alternatives like dark plasma.
And it's not just these observational oddities pointing this way. Computer simulations are actually backing it up too. Advanced models of cluster mergers suggest that if dark matter does indeed possess this hidden U1 charge we talked about, this sort of dark electromagnetism, it could naturally form collisionless shocks. It could exhibit plasma instabilities and even generate electromagnetic turbulence, all within the dark sector itself. These aren't just theoretical maybes. They are precisely the kind of dynamics we see in ordinary plasma.
That's a crucial point, yes, the agreement between theory and simulation. These effects mirror the known hallmarks of plasma dynamics that we see in visible astrophysical plasmas all across our universe. Think about Earth's bow shock, for example, where our planet's magnetic field slams into the solar wind, creating this turbulent plasma region. Or consider the incredibly complex energetic dynamics inside supernova remnants, where these expanding shock waves crash into interstellar plasma. The implication here is profound. Dark matter might exhibit strikingly similar collective fluid-like behavior under the right conditions, governed by its own set of fundamental dark forces. Theoretical models further propose that this dark plasma could directly influence how the vast cosmic filaments form, how the expansive voids grow, and how the halos around galaxies are shaped, all through long-range dark electromagnetic interactions, much like ordinary plasma shapes our visible universe.
Okay, now let's shift focus slightly to something visually striking, even though we can only really infer it through light bending. These concentric shells around some galaxies. When astronomers use gravitational lensing to map out the dark matter halos around elliptical galaxies, they often reveal these faint but, well, unmistakable concentric shells. And these aren't just small ripples either. We're talking structures on a truly grand scale.
That's absolutely right. These are genuinely massive structures. They extend 2, maybe even 3 times farther out into space than the bulk of the starlight we can actually see directly. And remarkably, in some cases, astronomers have found as many as 20 distinct shells surrounding a single bright galaxy. We have fantastic examples in galaxies like NGC 7600 and NGC 3923. They clearly show these features. In fact, roughly 1/10 of all elliptical galaxies are specifically classified as shell galaxies, precisely because of these distinct concentric structures. They aren't some extreme rarity. They're a recognized, albeit still somewhat mysterious, feature of the cosmos.
It paints a really beautiful image, doesn't it? Kind of like ripples spreading out on a cosmic pond across light years. Now, the prevailing theory for how these stellar shells form is that they develop when a large galaxy gravitationally merges with a smaller one. As the centers of mass of these merging galaxies oscillate around each other, they're thought to send out gravitational ripples, like waves. These waves then sweep through the star populations, creating these fanning concentric shells of stars. It's a compelling story, right? A dynamic dance of gravity. But this deep dive, following J. Alfred's work, suggests there might be another, possibly more fundamental, layer to this explanation.
Exactly. J. Alfred offers a compelling alternative hypothesis here, one that aligns perfectly with his dark plasma model. He proposes that these concentric shells aren't solely or maybe even primarily stellar phenomena created by gravitational waves from mergers. Instead, he suggests that the underlying dark matter halo, which is far more massive and extensive, remember, is itself composed of dark plasma. And this dark plasma, through its own intrinsic plasma dynamics, things like dark density waves, maybe collective electrostatic interactions within the weakly charged dark matter particles, it naturally organizes itself into these very concentric shells. It could be a fundamental property of how plasmas can structure themselves under certain conditions.
And then this is the really mind-bending part for me, through gravity. Through the gravitational interactions between this structured dark plasma and the ordinary matter. These dark concentric shells would essentially act as a colossal gravitational template. They provide the foundational mold, guiding and shaping the distribution of ordinary matter stars into a corresponding visible pattern. It's almost like the dark plasma is the invisible sculptor carving out the architecture of the visible galaxy.
That's precisely the template idea, and it's a crucial element of the hypothesis. J. Alfred himself actually noted this possibility quite early on, way back in 2005. He stated, and I quote, "The presence of shells in dark matter around galaxies suggests its plasma state. This is strong evidence that dark plasma is involved in interactions which can be modeled by using standard plasma." So his early insights were clearly pointing towards a dynamic, plasma-driven origin for these structures. It suggests that what we see in the visible universe might just be the gravitational imprint of a much more active and organized dark matter scaffold underneath.
Okay, moving from those elegant, almost static-looking shells to something far more energetic and dynamic, let's talk about vortical structures, specifically shock fronts and Mach cones. These are incredibly powerful phenomena, usually associated with supersonic flows in fluids and plasmas, and now we're seeing these tantalizing hints of them in the dark universe too. Back in 2015, there was a team led by the Finnish physicist Matti Heikenheimo. They did a rigorous study of the merger of the Abel 520 and 327 clusters, those same clusters we mentioned earlier, the train wreck cluster.
Yes, Heikenheimo and his team were specifically looking for signatures that might indicate dark plasma. He noted that, quote, "A generic prediction of the dark plasma model is the existence of the bow-shaped dark matter shock fronts, which should be visible in the weak lensing reconstructions of the cluster merger events given sufficient angular resolution." But crucially, he and his team went further. They suggested that these predicted effects might have already been discovered in the very Abel 520 and 327 clusters they were analyzing, essentially matching theoretical predictions with existing observational data.
Wow. And building on that, another team, this one led by Christian Spethman, also studying these really complex cluster mergers, they made a truly critical observation. They noticed that the precise position of the dark core within these mergers coincides remarkably well with the X-ray emitting gas, the hot ordinary matter plasma. Now, that's not a coincidence you can just easily dismiss, right? This direct spatial link led them to a groundbreaking hypothesis that maybe a subcomponent of dark matter isn't passive at all, but might be dynamically similar to the baryonic, i.e. ordinary matter plasma.
This is a direct observational link that provides really powerful support for the dark plasma idea. Spethman's team proposed that this newly identified dark matter component, which they also dubbed dark plasma, is capable of forming shock fronts that dissipate energy, behaving in a strikingly similar way to the baryonic plasma we see in the intracluster medium during these violent mergers. What's truly fascinating here is this almost one-to-one parallel between the observed behavior of dark matter and the well-understood dynamics of ordinary plasma. It strongly hints at maybe a shared fundamental nature in their collective behavior, even if the particles themselves are totally different.
And their detailed computer simulations, they showed even more, right? When they actually included this interacting dark plasma component in their models, it then naturally forms Mach cones. These are like distinct vertical structures, right? Signature features you see in magnetized plasma whenever something moves through it faster than the local sound speed in the plasma. You can almost picture them like the cosmic version of sonic boom cones trailing a supersonic jet, but made by streams of dark matter rushing through the dark plasma medium, may be guided by dark magnetic fields.
Exactly. The fact that these sophisticated simulations, when you incorporate a dark plasma component, naturally reproduce structures like Mach cones and shock fronts, that provides powerful theoretical support, and it dovetails perfectly with the observational hints we're seeing. It really strengthens the idea that dark matter's behavior is far more complex and dynamic than a purely collisionless model would suggest. And, it's important to place this in historical context, too. J. Alfred was already using the term dark plasma back in 2005-2007 to describe dark matter particles in a plasma state, especially near ordinary matter, specifically in connection with his dark plasma hypothesis. This was well before many of these specific observational studies and simulations really gained prominence, which highlights the prescience of his theoretical framework.
All right, moving from individual clusters now to the truly grandest scales of the universe. Let's zoom way out and talk about the cosmic dark matter web with its incredible network of filaments. This isn't just some pretty picture from a simulation. It's understood to be the fundamental, large-scale structure of the cosmos. It's the vast, interconnected scaffold upon which everything else is built.
That term, cosmic web, it was famously coined back in 1996 by Richard Bond at the University of Toronto, precisely to describe this vast, tangled structure, clumps, sheets, filaments that dark matter naturally forms over cosmic time. And scientists first got their initial tantalizing hints of this huge web by meticulously studying the cosmic microwave background, the CMB.
Right, the CMB. That ancient, faint afterglow of the Big Bang. It actually contains these tiny, tiny variations in density and temperature. These minuscule quantum fluctuations, imprinted on the universe when it was just an infant, they were the initial seeds from which all cosmic structure eventually grew. These variations implied that dark matter and the ordinary matter that was gravitationally pulled towards it, well, it should be unevenly distributed as the universe expanded and cooled. This natural process leads inevitably to the formation of highly dense regions, where galaxy clusters eventually form, and these vast, relatively empty voids in between, stretching for hundreds of millions of light years.
And to help you really visualize this cosmic evolution, consider this analogy from the source material. Imagine you have a piece of pancake dough, and you start stretching it from all sides simultaneously. As the dough stretches thin, large holes will inevitably start to appear in the less dense regions, breaking up the continuous sheet. What's left behind will be these delicate, thread-like structures of dough, winding their way around the empty spaces. This is actually a remarkably helpful mental picture for understanding how the cosmic web forms a universe being stretched, revealing its underlying filamentary and void-filled nature.
That's an incredibly vivid analogy, really helpful. And to go beyond just predictions and analogies, cosmologists didn't just stop there, did they? They used the power of incredibly sophisticated computer simulations. They took vast amounts of real galaxy survey data, extrapolated it using complex network algorithms, all to visualize this spongy, interconnected cosmic web. And these simulations have consistently revealed this intricate, almost biological-looking network of intersecting filaments made mostly of dark matter, with these enormous, largely empty voids scattered throughout.
And critically, it's not just simulations anymore. Over the past decade or so, various observational techniques, especially using the subtle distortions of gravitational lensing, where the gravity of massive unseen structures bends the light from distant background galaxies. These techniques have now powerfully, and I'd say unequivocally, confirmed the existence of this dark cosmic web. It is no longer just a theory or a simulation output. It is an observed, fundamental reality of our universe's large-scale structure.
And this dark cosmic web, it isn't just a passive backdrop, is it? It's an active gravitational shaper. It dictates the large-scale structure of the ordinary matter universe we see. It acts as a kind of cosmic skeleton, ordering galaxies and galaxy clusters, drawing them gravitationally along its filamentary paths. When we map out the universe, we find that most galaxies, including our own Milky Way, are found lining these dense filamentary structures, while the vast voids are, well, truly vast and empty, comparatively speaking.
Precisely. And the intrinsic properties of dark matter itself, things like its interaction strength, its thermal characteristics, whether it's cold or warm, these properties profoundly influence the sizes, the densities, the overall distribution of these filaments and voids. These dark matter characteristics, in turn, directly affect how visible ordinary matter galaxies end up being scattered and organized throughout the universe. So understanding the nature of this dark cosmic web, potentially its dynamic nature, is absolutely fundamental to understanding the universe we can actually see.
Okay, so we've laid out the core idea of dark plasma. We've looked at some pretty compelling observational evidence for plasma-like dynamics and structures within dark matter. We've discussed the vast architecture of the cosmic web itself. Now, let's tie it all together. This profound concept of the dark plasma universe acting as the ultimate active template for the ordinary matter universe. This is where the hypothesis really gets revolutionary, I think.
Right. On these cosmological scales, if you apply the basic principles of plasma dynamics, a dark plasma could profoundly influence how structure forms. It wouldn't just be passive gravity, it could exert its own internal pressure and viscosity, which would naturally tend to suppress the clumping of dark matter on smaller scales, potentially solving some existing tensions in cosmology. Crucially, it could dynamically form the dark filaments and dark shocks we talked about earlier, creating structure within the larger cosmic web, but operating entirely within the dark sector itself first.
And then, these incredibly massive dark structures, the filaments, the shocks, the shells, they wouldn't just be isolated phenomena in the dark sector. They would act as a kind of gravitational blueprint, wouldn't they? Shaping the ordinary matter structures around them through their powerful and pervasive gravitational forces. It's like the gravitational field coming from these organized dark sectors provides the cosmic instructions, guiding where galaxies and clusters end up forming. But it's not just a static blueprint, you're saying. It provides hidden dynamics.
Yeah.
It's potentially far from static. These dark plasma structures could also introduce hidden dynamics into the cosmos. They might offer an additional, maybe subtle, but potentially significant cause for the observed rotation of astrophysical objects, things like galaxies or even galaxy filaments themselves, that goes beyond what we currently attribute solely to gravity and angular momentum conservation. This raises a really important question. If the very template of the universe isn't just a passive gravitational well, but a dynamic, maybe rotating, actively interacting plasma, what are the full implications for the forces we measure? How might that change our understanding of phenomena like galaxy rotation curves or the strange alignments we see in large-scale structures? It suggests a far more complex and active interplay.
Wow. So, okay, if there's this massive cosmic dark matter web, and if the dark matter within it is fundamentally in a plasma state, then it logically follows that the incredibly long threads of this web, the ones we see in simulations and infer through lensing, they must themselves be composed of dark matter in a plasma state. Our ordinary matter universe, with its galaxies and gas, would then just be sort of draped over this invisible dynamic scaffold pulled there by gravity.
That's the powerful core inference of the hypothesis, yes. And due to these potential inherent dark plasma dynamics, these dark filaments of the cosmic web wouldn't simply be static structures. They could possess internal motion, possibly even rotation. And in rotating, they would subtly but powerfully tug on the ordinary matter filaments that are gravitationally bound to them, causing those visible filaments of galaxies and gas to rotate as well. It suggests this vast cosmic dance between the visible and the invisible, orchestrated by the fundamental dynamics of dark plasma. This could offer an intriguing explanation for some of the observed alignments and coherent rotations of galaxies across enormous distances.
That's an incredible vision, not just a static blueprint, but a spinning, dynamic blueprint, actively influencing everything it touches in the visible universe. And as we've discussed, there's this growing body of evidence that seems to support this template idea, from the vortexes, the Mach cones, the shock fronts seen in merging dark matter clusters, to the elliptical galaxies showing those traces of concentric shells that seem to beautifully map out underlying dark plasma dynamics. It all seems to consistently point toward the universe shaped by something far more dynamic than we previously thought.
And you can extend this concept even further. Just like in ordinary plasma, where we see electric currents flowing along magnetic field lines, think Birkeland currents in Earth's magnetosphere. The flows of dark plasma would likely be similarly guided if dark magnetic fields exist. This suggests the possible existence of what we might call dark Birkeland currents. Imagine these as immense dark rivers of dark plasma flowing along dark magnetic field lines across the cosmos. Through gravity or maybe even weak dark electromagnetic interactions, they could literally drag ordinary plasma along with them. This could be a profound mechanism for connecting structures and transferring energy and momentum between the dark and ordinary sectors over truly vast cosmic distances.
So on this truly grand scale, how similar are these dark sectors to our ordinary matter sector then? If most matter in both really exists in some kind of plasma state, what are the key points where they converge and where they diverge?
Well, in many fundamental ways, the dark sectors could indeed mirror the ordinary matter sector, particularly in the idea that most of their matter might exist in a plasma state. That's the unifying view. However, there are crucial differences that would define the unique characteristics of dark plasma, according to this hypothesis. Firstly, the rate of ionization in dark plasma might be much higher than in ordinary plasma, perhaps due to lower recombination rates or different fundamental energy scales involved in the dark sector. Secondly, and this is very important for structure stability, because of the proposed weaker dark charge, plasma instabilities would likely be significantly suppressed compared to ordinary plasma, less chaotic energy release. And thirdly, the suppression of instabilities combined with its unique charge properties might allow charge separation to be sustained more effectively and for longer periods in dark plasma. This could be critical for forming the stable, enduring structures like the concentric shells or the cosmic web filaments that seem to persist over billions of years.
Now, this is really important, I think, to avoid any confusion, especially in these cutting-edge discussions where terms can get easily mixed up. We need to be absolutely clear about what dark plasma is not.
Absolutely critical. When we discuss dark plasma as proposed by J. Alfred and other prominent researchers who've explored similar ideas like Sean Carroll, Lottie Ackerman, Matti Heikenheimo, Christian Spethman, Nitin Shukla, we are specifically exclusively referring to a plasma made of dark matter particles. These are hypothetical particles that exist outside our standard model of particle physics. It is emphatically not a plasma made of ordinary matter particles, protons, electrons, ions that are simply in what's sometimes called a dark mode. This distinction is absolutely non-negotiable for understanding the hypothesis correctly.
Right. And just to spell that out, plasma in dark mode would refer to a plasma made of ordinary matter particles, the stuff we know, that just happens to radiate very little light. Maybe it's extremely cold or extremely diffuse, making it invisible to our telescopes. It's incredibly easy to get these two very different concepts mixed up, but their fundamental composition, the particles they're made of, are profoundly distinct. One is known stuff that's hard to see, the other is completely unknown stuff.
And there's incredibly strong cosmological evidence against the idea that the huge structures we're talking about, the massive dark matter halos, the cosmic web filaments, could possibly be composed of ordinary matter in some kind of dark mode. Gravitational lensing reconstructions clearly show these structures are immense, many times larger and vastly more massive than all the visible ordinary matter structures combined. If these colossal structures were made of ordinary standard particle matter that was just dark, it would directly contradict a whole range of results from rigorous analyses of the cosmic microwave background power spectrum. It would also contradict data from Big Bang nucleosynthesis, primordial element abundances, and large-scale structure observations. For instance, the CMB power spectrum precisely tells us the total amount of baryonic or ordinary matter in the universe. If these huge dark structures were baryonic, they would have left unmistakable acoustic signatures in the CMB, different from what we see. They're just not there. This is why that possibility is definitively ruled out by cosmologists. And this raises an important point. Without these incredibly precise distinctions and robust evidence backing them up, the entire theoretical framework for the universe's composition could just crumble. Precision and clarity are absolutely key in these frontier areas of physics.
Precision is paramount, you're absolutely right. So let's explicitly break down some of the fundamental differences between ordinary plasma and dark matter again, just to really hammer home why they are fundamentally separate things, even if both might exist in a plasma state in their respective sectors.
Certainly. Let's recap. Ordinary plasma, the stuff we know, is fundamentally made of charged particles, electrons and ions, and its interactions are governed entirely by our familiar force of electromagnetism. That's why you find it in stars, lightning, neon signs. And because it's charged and interacts electromagnetically, it emits light, visible, X-ray, radio waves, making it detectable by our telescopes across the electromagnetic spectrum. Dark matter, on the other hand, is primarily defined by its invisibility to electromagnetic radiation. It fundamentally doesn't emit, absorb, or reflect light in any significant way. That's why it's dark. We can only detect its presence indirectly, through its gravitational effects, how it bends light via lensing, or how it influences the rotation speeds of galaxies. It remains stubbornly silent electromagnetically.
And the cosmic microwave background, the CMB, that really offers another major, almost irrefutable piece of evidence differentiating ordinary plasma from dark matter, doesn't it?
It's perhaps the most definitive proof, yes. The early universe, for its first few 100,000 years, was this hot, dense soup of ordinary plasma, where photons were constantly scattering off charged electrons and protons. When the universe cooled enough, photons decoupled from this matter, creating the CMB radiation we observe today. Now, if dark matter were just ordinary plasma, it would have been electromagnetically coupled to this early photon baryon fluid. It would have left clear, specific electromagnetic imprints in the CMB's pattern of temperature fluctuations, its power spectrum, but it didn't. The CMB precisely shows the expected signatures of baryonic, ordinary matter interacting with photons, but no equivalent electromagnetic signature for the far greater amount of dark matter. Furthermore, ordinary plasma, because of its high internal pressure from particle collisions and heat, strongly resists gravitational collapse on large scales. Dark matter, being cold, meaning slow-moving, and traditionally considered collisionless or weakly interacting, lacks the significant pressure support. This allows it to efficiently clump together under gravity, forming the deep potential wells, the scaffolding for galaxies and larger structures to form within. Ordinary plasma would behave entirely differently under those same conditions. It couldn't form such large, stable structures so early or efficiently.
Okay, so just to be absolutely crystal clear and reiterate, we're also not talking about some kind of dark plasma made of ordinary matter particles that might exist, say, deep inside the sun, which looks dark to us just because it's cooler or denser than the surface. This dark plasma we're discussing today, the one hypothesized by J. Alfred and others, it's a wholly different beast composed of completely different particles governed by potentially different fundamental forces.
Precisely. Dark plasma, or dark matter plasma, as this hypothesis describes it, is a self-interacting medium governed by a hypothetical independent dark electromagnetism. Even with these internal interactions, it wouldn't magically become ordinary plasma. It would interact via its own dark forces, not the electromagnetic force we know, and it would still remain utterly invisible to our instruments, unable to emit or absorb ordinary light. So the distinction is absolutely fundamental. Even if you talk about ordinary plasma being in a dark mode, that's still ordinary matter. Dark matter plasma is an entirely separate category of existence. One glows, even faintly or indirectly, the other hides completely. One resists collapse, the other builds galaxies. Grasping this distinction is critical for this whole deep dive.
So, okay, well, taking all this in, what does it mean on the grandest, most mind-boggling scale? If this dark plasma hypothesis holds true, what are the fundamental composition of plasma in the entire universe, or even what J. Alfred calls the local multiverse, truly look like?
Well, J. Alfred's paper reaches a truly grand conclusion based on this framework. Broadly speaking, it suggests that dark matter is generally in a plasma state across the cosmos. And since we know practically all the ordinary matter in our sector is also, fundamentally, in a plasma state, from stars to intergalactic gas, then we can broadly assert that the whole of the universe, or what Alfred terms the local multiverse, is fundamentally in a plasma state. He defines this local multiverse as composed of our ordinary matter sector and all other dark sectors that are gravitationally coupled to it. It paints this picture of an enormous, interconnected, dynamic cosmic soup of charged particles.
Wow. So if this hypothesis really holds water, we're essentially living inside an enormous, all-encompassing plasma soup, visible and dark, all intertwined and interacting.
Yeah.
With an incredible mental image that really challenges the standard view. But it's not all the same kind of plasma, right? The paper breaks it down into different types based on this model.
That's a crucial nuance, yes. Distinguishing how different components of this vast cosmic plasma actually behave. J. Alfred's paper offers a detailed breakdown of the universe's matter composition according to this view. Firstly, there's what he calls pseudoplasma. This makes up a massive 70% of all matter in the universe, combining both dark and ordinary components. It's described as a highly diffuse soup of elementary particles. Now, while it possesses some fundamental plasma characteristics, like being largely ionized, its particles are typically so incredibly far apart that they don't exhibit the complex collective signature features of active plasma, things like generating strong magnetic fields, supporting plasma waves, or having significant self-interactions, unless it happens to be in the immediate vicinity of more active, dense plasma. It's presumed to be mostly neutral overall, like the vast, tenuous gas in the intergalactic medium. Its role is largely passive, but it's still fundamentally ionized matter.
Okay, 70% pseudoplasma. And within that, or perhaps alongside it, there's also a component called dormant dark plasma.
Correct. Dormant dark plasma is also composed of charged dark matter particles. Like the pseudoplasma, these particles are typically so far apart, perhaps residing in the vast voids of the cosmos, that they don't actively interact in a collective dynamic way most of the time. They are potentially self-interacting, meaning they could interact if they were brought closer together, but they don't generally exhibit the signature features of active dark plasma unless they find themselves near dense ordinary matter or regions of active dark plasma. You can think of it as the quiet, largely unseen majority of the invisible universe, sort of waiting for the right conditions to become dynamically active.
And then we get to the truly active players, the ones doing the real shaping and interacting in this picture.
Exactly. Then we have actin dark plasma. This component is estimated to make up a significant 15% of the total matter in the universe. This is specifically a plasma of self-interacting charged dark matter particles. It's found in more dense environments, usually in the vicinity of ordinary matter, think inside galaxy halos or along the dense cosmic filaments. Here, the dark matter particles are close enough to collectively interact, forming dynamic structures, exhibiting those plasma behaviors like shocks or instabilities that we've discussed. And then finally, we have active ordinary plasma. This constitutes another 15% of the matter in the universe. This is the plasma we directly observe in stars, in hot galactic gas, and active galactic nuclei. It's the luminous, energetic component of our familiar universe.
So hang on, if you add up the active dark plasma, 15%, and the active ordinary plasma, 15%, that comes out to a substantial 30% of the total matter in the universe being actively self-interacting and exhibiting these dynamic plasma behaviors, shaping everything around it. That paints a picture of a truly dynamic universe, fundamentally driven by plasma interactions, both visible and invisible.
Exactly. If we connect this to the bigger picture, this detailed breakdown suggests a highly structured and nuanced distribution of plasma states throughout the cosmos. It's not simply a binary plasma or not plasma situation, it's a spectrum of activity. It adds these profound layers to our understanding of the universe's overall composition. It posits that a very significant portion of both visible and invisible matter isn't just passively sitting there, but is dynamically active, constantly interacting, and fundamentally responsible for the cosmic architecture we observe. This suggests a universe far more alive, far more interconnected than we perhaps once conceived.
Wow. Okay, so we've journeyed through the ghost universe today, only to find it might not be so ghostly after all. It might be a living, breathing plasma, dynamically shaping everything we know and see. We've explored J. Alfred's compelling dark plasma hypothesis. We've delved into the surprising observational evidence from galactic shells and cluster mergers that strongly seems to hint at this. We've understood the concept of a dynamic cosmic web, and we've carefully clarified the crucial distinctions from ordinary plasma to try and prevent any misinterpretations. This deep dive has truly opened up a whole new way of thinking about cosmic structure for me. And for you listening, this deep dive hopefully offers you a powerful new lens through which to view the cosmos. A perspective where the invisible isn't just dark and inert, but potentially dynamically active and absolutely foundational to our very existence. It fundamentally challenges us to rethink the very nature of matter, the forces at play on the largest scales. It suggests a universe far more integrated and responsive than we previously imagined. The universe isn't just a collection of objects. Maybe it's a vast, flowing, charged system.
And this raises a really important question, doesn't it? If this dark plasma template isn't just a static blueprint, but is actively rotating, interacting, maybe even evolving, how might that ongoing, dynamic interaction truly sculpt the future evolution of the cosmos itself? It opens up possibilities for understanding cosmic development that are far more dynamic and complex than purely gravitational models might suggest. It could even influence the ultimate fate of galaxies and clusters in ways we haven't considered.
And thinking even bigger, if the entire universe, visible and invisible, is fundamentally this vast interconnected sea of plasma, both dormant and active, what other cosmic phenomena might eventually be explained by these hidden dark electromagnetic dynamics? And what profound implications might this have for the search for life, or even our understanding of the nature of consciousness itself, if everything is, at its most fundamental core, perhaps a form of charged, self-interacting energy? That's something truly profound to ponder the next time you find yourself looking up at the night sky. Until our next deep dive, keep questioning, keep exploring, and stay curious.